Hello, my name's John Ray Rao, and today I'm going to present my final project for EE320 Lab. So basically, first I'm going to go over what logic gates are, what MOSFETs are, and how I made the MOSFETs into the logic gates basically. I'm also going to go over some theory, the results, demonstration, the problems I encountered, and solutions, and the conclusion. So logic gates are basically electronic circuits that take a 1-bit input, or actually two 1-bit inputs, and produces a 1-bit output. And so for this final project, I'm gonna create a NOT, a NAND, an OR, and an XOR. And by the way, the 0 and the 1 in LT Spice, 0 is 0 volts and 1 is 5 volts. So MOSFETs, which stands for metal oxide semiconductor field effect transistor. There are two types. There's the NMOS, which is the N channel, and PMOS, which is P channel. And there's also CMOS. Basically, it's a combination of both. They're complementary. And the basic symbol here, in terms of the terminals, they have a gate, a drain, a source, and a body. This is also another symbol that I'm going to reference for NMOS, and this one too for PMOS. And I'll go over in more detail, but basically they act like switches that operate based on the voltage at the gate. So it's unlike the BJT, or the bipolar junction transistor, which operates which controls a current based on it's a current controlled current source, but the MOSFET is a voltage controlled current source. And so in terms of how you would put the MOSFETs together, they're always in a CMOS complementary fashion. In fact, the NAND here, it has the PMOS in parallel and then the NMOS in series, and it's always like this. When NMOS is in series, PMOS is in parallel. When NMOS is in parallel, PMOS is in series. And so this is just how it should look like in terms of the schematic. I'll explain more how this operates. But you can use these basic gates, the NOT, the NAND, and the NOR, to produce AND and OR, because AND is just not NAND, and OR is just not NOR. And also you can use AND and OR to produce XOR, which is A NAND B and A OR B. It's useful to see it in the gate level, because you're basically taking the components and just putting them together. In fact, that's what I did here. So it builds up in terms of layers of abstraction. It just keeps building up, and it's easier to understand that way using components. So the relationship between the voltage and the current is listed here. So there's a cutoff region, the linear region, the saturation region. So basically, depending on the voltage from gate to source, determines the current running from drain to source. So for example, if it's less than the voltage threshold, then it's 0, which just means it acts like an open switch. And when it's greater than, then it becomes a closed switch almost. In fact, if you keep increasing it, it goes into saturation, where it can't increase the current anymore. So this is just a diagram showing that relationship between the voltage at the gate and the current. So as you can see here, when it's below the threshold, there's no current running through. But when there becomes some it reaches over the threshold, you see the current, it starts to gradually rise, but it becomes linear, and then it goes to the saturation region. So it basically can't increase the current anymore unless you increase VGS and VDS. And so this is also the PMOS. So this was NMOS. The only difference between NMOS and PMOS is that the voltages required are negative. The current is also negative, so instead of going from drain to source, it's going from source to drain. And so I wanted to show that happening in LT Spice before I go into the digital logic circuits. Just a demonstration of the behavior of NMOS versus PMOS. So basically, you can think of it as acting like a switch in both cases. But when the voltage at the gate it reaches over the threshold, the NMOS, it acts as a closed switch, so it connects to ground. But the PMOS, it acts as an open. It's basically connected to VCC. As you can see here, when it's 1, NMOS is closed, but when it's 1, PMOS is open. And the opposite happens finally when VN gets closed. VN becomes 0, so NMOS would become open, so now it's VCC, and PMOS would get closed, so it'd have connection to ground. And that's what happens here. It becomes 0, this becomes 1. And so, in short, you can think of NMOS conducting only when it's over the threshold, but not when it's below. But for PMOS, it's the opposite. It doesn't conduct when it's over the threshold, but it does conduct when it is below the threshold because of the negative voltages and the negative current. And so, basically, you can think of this. It's easy to see it. The MOSFETs operating by thinking of it as open and closed. So when A is 0, NMOS is closed. PMOS is closed and NMOS is open. So it gets a connection to VCC, so it becomes 1. And when it's 1, NMOS is closed and PMOS is open, so it gets a connection to ground. So when A is 0, it produces 1, and A is 1, it produces 0. So it's basically a NOT. And this is the NAND. So wherever you see red, it gets closed. So when it's 0, the PMOS gets closed. But when it's 1, PMOS gets open. And when it's 0, NMOS is open. But when it's 1, it's closed. So it's complementary in that fashion. So in parallel here, just one of the PMOS has to be closed for it to get VCC. And both NMOS have to be closed because they're in series to get 0. And so they produce this truth table where 0, 0 produces 1, 0, 1 produces 1, 1, 0 produces 1, and 1, 1 produces 0. And if you NOT that, that becomes 0, 0, 0, 1, which is the truth table for AND. So similarly, there's also NOR. Again, when it's red, it's closed, and when it's green, it's open. But this time, PMOS is in series, and NMOS is in parallel. And so both PMOS have to be closed, or A has to be 0 and B has to be 0 to get VCC. But only one of the NMOS has to be closed, or has to be 1, for it to get ground. So that's why it's 1, 0, 0, 0. So it produces this truth table, 1, 0, 0, 0. And if you NOT that, that becomes 0, 1, 1, 1, which is the truth table for OR. So these are the schematics. You can pause if you want to look at them. But basically it's everything I've talked about so far. So this is the truth table you would expect. The NOT and the NAND, the NOR, and the XOR. And basically also how the way they're structured. This is a NAND going to a NOT, producing an AND. A NOR going into a NOT, producing an OR. An XOR, and this is basically the XOR. So you get the product of sums, which is A NOT or B NOT and A or B. And then using, I think, De Morgan's law, you get A NAND B and A or B, which produces this circuit. And so this is just a demonstration of it happening. So it's a little bit fast, but I'll just pause. So this is the NOT, so when it's 1, it's 0. When it's 0, it's 1. That's what you'd expect. And then the NAND. So when it's 0, 0, actually the AND, this is the NAND, the green one, and the red one is AND. And you can see as 0, 0, it becomes 0, 0, 0, and it only becomes 1 when both are on. So that's what's happening here with the AND. Opposite with the NAND. And then we got the OR as well. Again, the NOR is in green and the OR is in red. So when it's both 0, 0 here in the inputs, you get 0. But when one of them is on, or at least one of them, you get 1. That's exactly what you'd expect. And then of course there's the XOR. So they're only on when there's only one on, basically. So when both are on, it's off. And both are off, it's off. So it's only when one is on, 0, 1, or 1, 0. So basically that's the demonstration. So in terms of the problems I had, basically I just needed to look online to see how it was getting produced. How do you put the MOSFET together to produce the logic gates? I also needed to connect the MOSFETs correctly, so I just needed, again, to look at the online. There were also abrupt spikes in my input, so I think that was because LT Spice was trying to calculate ahead of time, so there are these like discontinuities. So a smaller time step made sure that there were no abrupt changes. And I just learned a lot from this project. I reviewed the IV characteristics that we went over for NMOS and PMOS, but I also learned how the MOSFET acts as a switch to produce the logic circuits. I also learned how you can use abstraction and a hierarchy to produce not NAND nor to produce AND OR, which can produce XOR. And then you could keep going up to produce a microprocessor if you wanted to. And also I learned how they should be put together. Basically that they should be complementary logic, CMOS. And I learned and I enjoyed learning about it. And then also I'd like to acknowledge Ming Zhu for creating the labs and teaching us what we needed to do. And also the teaching assistant, Rojin Aslani, for giving feedback and the corrections on the lab. So basically these are the references, and yeah, that's all.